Okay. Hi, welcome to the pre-recorded lecture. So let me continue my unfinished proof. It's unfortunate I couldn't finish it last time. What I was doing is, so continued from last lecture. What I was doing is, so I have these Catalan numbers, right? Number of dig paths from 0, 0 to n, n. And I was trying to figure out a formula for the ordinary generating function for the Catalan numbers. So that's the goal, to find a closed formula for f of x. And the first step was to find the recurrence, which was recurrence which I found kind of bijectively is, it has a very simple form, just ci times cn minus I for I summing over I from 0 to n. And this recurrence, as I did in the last lecture, can be easily transformed by just multiplying by x to the n plus 1 and summing over all n. You get a relation for the generated function, which was of the form f of x minus 1 is equal to x times f of x squared. And what I ended up with is, well, I solved the corresponding quadratic equation, solved for f of x, and I got this weird formula. 1 plus minus square root of 1 minus 4x divided by 2x. And as I mentioned, the right-hand side does not quite make sense as a formal power series. Meanwhile, the left-hand side, f of x, is uniquely defined by, I mean, it's a specific generated function, right? F of x is like 1 plus x plus 2x squared plus 5x cubed plus etc. It's well defined. So I have to be more careful. And the way I'm going to be more careful is, okay, I'm gonna use this expression as a as an inspiration. So well, first of all, I can, even though it contains a square root, which may be scary. It might look scary, like why do we have square roots? So first of all, yeah, for the square root, you just compute the square root by the binomial theorem. 1 minus 4x is equal, by the binomial theorem, right? It's well, it's the same as 1 minus 4x to the 1/2. So it's the sum as a formal power series. Just by definition, it is 1/2 choose n, right? 1/2 being the power times, and yeah, since we have 4x to the n, we have, yeah, it should be just 4x. Yeah, it's negative 4x. Okay, negative 4x to the n by the binomial theorem. So that is, if I separate the negative 4 and the x into negative 4 to the n times x to the n, then this is a valid formal power series, right? For each x to the n, I have a coefficient which is whatever it is, right? 1/2 choose n. 1/2 choose n is what? Is 1/2 times 1/2 minus 1, etc. times 1/2 minus n plus 1 over n factorial. Yeah, it's going to be some rational number. So at least the numerator is all right. But the problem is when you divide by 2x, you know, 2x is not invertible. You can't divide by 2x. So let me write it down. 2x is not invertible. So that's a problem. Well, let me try to reorganize the terms a little bit. So instead of writing in this way, what I'm going to do is I'm just going to multiply by 2x. 2x times f of x minus 1 is equal to plus or minus square root of 1 minus 4x. So far so good. And notice that, okay, so here both sides make sense. Both sides are formal powers, are nice formal power series. And if you compare the coefficients well, yeah, since I made a non-rigorous step of solving a quadratic equation in formal power series, I cannot just right away conclude that f of x satisfies this equation. And in fact, I mean, there's two equations, right? One with the plus, another one with the minus. So I have to, first of all, I have to decide which sign is correct. So, and the easy way to do this is to compare the coefficients of x to the 0. So I want to compare the constant terms. And if I compare the constant terms, on the left-hand side, the coefficient is -1. Right? This gives me 0 constant term. This gives me -1. And for 1 minus 4x, if you look at the expansion, then what happens for n equals to 0? Yeah, let's see what happens for n equals to 0. Well, I mean, it should be 1, right? Let me try to write this down. So for n equals to 0, I have 1/2. Well, I actually have an empty product over 0 factorial. So that's actually 1 plus, and the next one is going to be negative. So for n equals to 0, I just get 1. For n equals to 1, I get -4 to the 1, the first, times x, and divided by 2, I guess, right? Because there is going to be 1/2 over 1 factorial, plus etc. And this should be familiar to you from calculus again. If you just try to find the asymptotics of this square root, this is the first term you're going to see. So anyways, the point is that the constant term is 1. So for the right-hand side, the constant term is plus or minus 1. So it has to be -1, because otherwise we have no chance of having these two equal to each other. Yeah. So our guess, so far we are only kind of guessing. Guess is that 2 times f of x minus 1 is equal to negative square root of 1 minus 4x. And it's actually, if you just square both sides, so from now on I'm being rigorous. You start with this equation and you square both sides and you get what you're going to get is, well, I mean, because we solved the quadratic equation correctly, what we're going to get is, I mean, I can just write it down. 4f squared minus 4f plus 1 is equal to 1 minus 4x. Wait, where is, sorry, there was a 2x. 2x f of x. So 4x squared f squared minus 4x times f plus 1 is equal to 1 minus 4x. So the ones cancel out, and then what I get is the same. What I get is equivalent to f of x minus 1 is equal to x times f squared. Is it? well, there's an extra x, right? So yeah, if I just divide both sides of this by 4x, divide by 4x, and I can divide, I mean, if all of these terms are divisible by 4x, then I can just pull it out of the summation. So in this, if they are divisible, I can divide. And what I get is just x times f squared minus f is equal to -1, which is the same as this thing, as the equation I got from recurrence. So the point is, the conclusion is that f of x satisfies, I mean, if I squared and anyways, I guess I'm being slightly non-rigorous again. But anyways, the point is that f of x satisfies 2x f of x minus 1 is equal to negative square root of 1 minus 4x. And therefore, f of x is 1 minus square root of 1 minus 4x over 2x. So that's the end of the proof, I guess. Yeah, I mean, I made a little, slightly non-rigorous step here, because I have to, if the squared power series are the same, then the power series have to be the same up to a sign. That's an exercise, I guess. I mean, it follows from the unique factorization properties of the ring of formal power series. So that's the end of the proof. And one, as I promised, now I'm supposed to explain how to get from here to the formula for, like, explicit formula for Catalan numbers. So question, how to deduce that Cn is equal to 1 over n plus 1 times 2n choose n. And the answer is you just expand the right-hand side. Because the right-hand side can be, yeah, which, by the way, so I don't know if I mentioned it, but this expression in the numerator, it has constant term is equal to 0, so it is divisible by x. And therefore, the right-hand side is an honest formal power series. I just pull x out of the summation, and then I cancel it with the x in the denominator. Yeah, so the point is that if you just expand the right-hand side, right, I have 1 over 1 minus this guy, so the square root, so I already know how to expand the square root. Yeah. I have an explicit formula for these binomial coefficients. So let's see, I actually have a correct formula here. Let's check if it agrees with, yeah, -4 times x over 2. That's the same as -2x. So it keeps, yeah. You can compute all the coefficients exactly by just some product formula like this. And then, because you're gonna get basically, you're gonna get odd numbers over 2 in the numerator. And then there's going to be a power of, there's going to be times 4 to the n. So instead of taking odd numbers, you get like double factorials. Anyways, after some simple manipulations, which I will leave as an exercise, you get this formula just by generating functions, which so this may not sound impressive to you because you already knew this formula from a bunch of lectures ago, but in general, if you have some mysterious sequence given by some recurrence or whatnot, and you want to find the formula. If you don't know the formula in advance, generated functions allow you to actually deduce this formula algebraically. And you're going to see this in the homework and the midterms. So yeah, these, especially if you can find a recurrence relation, then it's, once you have a recurrence, then you can just write down the generated function. But also mathematically, I think it's beautiful that you just get a nice closed formula. So Catalan numbers are special, and then they have this nice closed formula, which you wouldn't be able to guess in advance. So that's it. That's well, that's not it. So far I'm done. I have computed. So far, I have computed 1 plus 2x plus 3x squared plus etc. and Fibonacci numbers and Catalan numbers. But there's many more sequences we have seen in this class already. Like for example, maybe let's say partitions P of n, or maybe Bell numbers. For each of them, you can write down a generated function, an exponential generated function, and then you can ask what's going to be the formula. Is it going to be a simple, nice, closed formula, or is it going to be some sort of crazy, intractable thing? And today I'm going to focus on partitions. But to be able to work with them efficiently, I'm going to have to introduce introduce slightly some other piece of formal machinery to work with formal power series, and that's going to be using infinite sums and products. Yeah. So, which, by the way, all this business with generating functions was started by Euler in the 18th century, and he didn't really care to be exactly rigorous. So we're gonna be just like him, except that we're gonna actually do things. Well, we're gonna get the same. He got the correct answers, but the methods were not justified at that time. So we're gonna justify the methods. And remember, so previously we had an example where there was an example like exponential of x plus 1 is equal to e times the exponential of x. And on the left-hand side, if you just write down the Taylor series, you get n greater than or equal to 0, x plus 1 to the n over n factorial. And what I said was that this is not a well-defined formal power series, which is still true. It is not well-defined. But I would like to work with infinite sums. So I would like to have an infinite sum where each term itself is a formal power series. So I have to be careful because this one doesn't give me anything. So how do I? And the reason this one was bad was because each term contributes something to the constant term. Infinitely many terms in the summation contribute to a particular coefficient of my formal power series. I don't want that. So I want to, okay, so here's the way I'm gonna make this precise is using the minimal degree of a formal power series. Here's a definition. If you have a formal power series like this, just an x to the n, then I'm gonna denote the minimal degree of f(x) just by definition to be the minimum an such that, well, the minimum n such that an is not 0. So yeah, I just look at the first coefficient. If you give me a power series, I look at the first kind of the first coefficient which is not 0, so that's like the power of x which divides f of x. Yeah, and so I'm going to use this minimal degree to introduce the notions of stabilization. Here's another definition. So again, I'm going to talk about infinite sums and products in a second, but for now I'm just going to say when does a sequence of formal power series, I'm not going to say converge, because converge is already a word from calculus. I'm going to use the word stabilize, because it's better, it reflects the meaning better. So okay, let's say I have some formal power series, an x to the n. And then let's say you have another sequence. You have another sequence of formal power series, f1 of x, f2 of x, etc. Of formal power series. Then I'm going to say that the sequence stabilizes to f of x if, so what I'm going to require is that each individual coefficient for a given degree, so if for each n greater than or equal to 0, the sequence of coefficients, so the coefficient of xn in f1 of x, the coefficient of xn in f2 of x, etc. I want this sequence to stabilizes. So this is a sequence of complex numbers. Each coefficient is just a complex number, and I want it to eventually, like after a certain point, I want it to be just constant. So I want all terms to be the same and equal. Stabilizes to an, where an is the coefficient of the corresponding coefficient of f of x. So stabilizes to an means that all terms become equal to an after finitely many steps. So in other words, again, I never want to worry about convergence of some infinite series like I had here. So I want this process to terminate after finally many steps. So you give me an infinite sequence of formal power series, but if I'm only interested in like the coefficient of x cubed, then I have to, after finally many steps, I'm going to see just the same coefficient of x cubed in all of your terms. And then you can define the limit. So I'm going to write that the limit as j goes to infinity of f sub j of x is equal to f of x. And let me emphasize this is not the usual calculus limit. This is a much weaker notion. I just want, or much stronger. I want all coefficients to be exactly equal to an after finitely many steps. That's the difference. So, and now, similarly to calculus, once I have the notion of a limit, I can define let's say I can define infinite sums. So just by definition, well, let me actually state it as a definition. This definition is that we write the infinite sum of formal power series is equal to another formal power series if, so again, by definition, the limit m goes to infinity of the sum of j from 0 to m f sub j of x. So the limit of this expression is equal to f of x. This thing here is a finite sum of formal power series. So it is itself, so each individual term here is a formal power series, just as in this definition here. So I want the sequence of these formal power series to stabilize to this formal power series. So that's the definition of an infinite sum. And another, so here's a definition of an infinite product. Here, for infinite products, I'm going to assume that the constant term of each term in the product is equal to 1. And I'm going to write it in this way. So if I have power series G sub j each without constant term for all j greater than or equal to 0, then we write an infinite product of j greater than or equal to 0, 1 plus g sub j of x. This infinite product is equal to f of x if, again, the same limit, except that I have to put a product instead of a sum. Or maybe I should write g of x. Oh, yeah, no, let's write f of x. Okay. So instead of the sum, I'm taking the product for j up to m as before. And instead of f, I'm going to write g. No, actually, instead of f, I'm going to be careful here. Instead of f, I'm going to write 1 plus g sub j of x. So again, right, if I want to take an infinite product, then I just ask that all these finite products, each finite product is a formal power series, and I want them to stabilize to f of x. Okay, so you may ask, how do I check? How do I check if you give me some infinite, let's say infinite sum, how do I check that it stabilizes to f of x? That seems like a lot of work. You have to compute all these infinitely many coefficients. So here's an easy criterion to make sure that an infinite sum and an infinite product stabilize to to something. Right? I'm not even gonna tell you what f of x is. I'm just gonna give you a criterion. So an infinite sum, j from greater than or equal to 0, f sub j of x, stabilizes to something. Stabilizes if and only if the limit of the minimal degrees of fj of x, so this limit, is equal to infinity. And similarly, that's the first part. The second part, if you assume that all these g sub j of x have 0 constant term, then the infinite product j of 0 to infinity 1 plus g sub j of x stabilizes if and only if the same condition on the minimal degree holds. Except I have to write g sub j of x. And this is very easy. I mean, it's just what does this condition mean here? It means that after finally many steps, for each n, after finally many steps, the minimum degree of the terms becomes bigger than n. Should I write it down? This means that after, so for each n, yeah, for each n, after finitely many steps, the coefficient of x to the n in f sub j of x is 0. Just by definition, at some point the minimum degree becomes bigger than n, and so all these coefficients are going to be 0. So there's going to be for each n, there's only finitely many terms which contribute to the coefficient of x to the n. So it has to stabilize if and only if the minimum degree goes to infinity. Yeah, so I'm not going to prove it, but the proof is straightforward just from definition. Yeah, let me just write exercise. And maybe it feels a little unclear, but if I do actual examples here, I'm gonna see what happens and why do some products stabilize and some don't. So here is the first example, which is slightly tautological, but examples. So let's say I have a sequence of, let's say I say fj of x is equal to just a single monomial, a sub j times x to the j. For j greater or equal to 0, then I can take the sum. I can take an infinite sum of f sub j of x. I treat each of them as a formal power series. So if I write down this infinite sum, then I can use the criterion. Where is it? Yeah, the criterion is that the minimum degree has to go to infinity. Well, the minimal degree of f sub j of x is equal to j, which goes to infinity as j goes to infinity. Therefore, this sum stabilizes. So the sum stabilizes to what? Well, it stabilizes to, as you can imagine, sum a sub j x to the j, but now this is treated as a single formal power series. So it's a little confusing, but on the one hand, this is a sum of individual formal power series. On the other hand, it is just a single formal power series. That is example number 1. Here's another example which generalizes what we did with the generalized binomial theorem. So if f is any formal power series without a constant term, and alpha is any complex number, I can now define formal power series 1 plus f of x to the alpha. Again, using the same generalized binomial coefficients as from the previous lecture. And okay, so indeed, and now I have to check whether, I cannot just define it. I have to check that the infinite summation stabilizes. Well, okay, I can do that. Right? The minimal degree of f of x to the n is just because f has the minimum degree of f is at least 1. It is greater than or equal than n. And therefore, this summation stabilizes. In other words, to compute the coefficient of x cubed, you only have to consider the first three terms, because after that, it's not going to contribute to x cubed. And now, again, this satisfies all the usual rules, like if you multiply two expressions, then the degrees are going to add up, and etc. So, and I'd like to maintain that the original non-example is still a non-example. So the sum of n greater than or equal to 0, x plus 1 to the n over n factorial does not stabilize. Because, well, why? Because the minimal degree of each individual term of x plus 1 to the n, where n factorial is equal to 0, it does not go to infinity. And yeah, so now that I'm equipped with the machinery of infinite sums and products, let me try to tackle partitions. Because remember, P of n is the number of partitions of n. So for example, 5 is equal to 4 plus 1, equal to 3 plus 2, 3 plus 1 plus 1, 2 plus 1 plus 1 plus 1, 1 plus 1 plus 1 plus 1 plus 1. These are all possible partitions of 5. So I want to find, goal is to find, so you have f of x to be, just you can define it as usual, to be the ordinary generating function. And the goal is to find the formula for f of x. Now, okay, as you may expect, this formula is going to involve either an infinite sum or an infinite product. Well, in fact, this is already an infinite sum, so that may already be satisfactory to you. But the point is that these numbers are hard to compute exactly. So it would be nice to have some formula which is some infinite product or sum where each individual term is easy. Here's the formula, which I think is very nice. F of x is equal to, again, if you had to guess it, that would have been, the only way to guess it is to actually prove it, can deduce it from common sense. The formula is just the infinite product of 1 over 1 minus x to the j, where j runs over all possible integers from 1 to infinity. Here's the proof. Well, maybe before I do the proof, let me try to expand this product a little bit. As you remember, 1 over 1 minus x to the j is 1 plus x to the j plus x to the 2j, x to the 3j, etc. So if I write down the first several terms in this product, what am I going to get? Get 1 plus x squared plus x cubed plus etc. That corresponds to j equals to 1 times 1 plus x squared plus x to the 4th, x to the 6th, etc. 1 plus x cubed plus x to the 6th, x to the 9th, etc. and etc. That's my infinite product. It goes on forever. But if I'm only interested in the coefficient of x to the 5th, then there's going to be, at some point, right after some time, I'm going to have 1 plus x to the 100 plus etc. And I can't take x to the 100 to, it's not going to contribute to the coefficient of x to the 5th. So I can just discard all, whenever I'm interested in a finite coefficient, I can discard most of the terms. I can only focus on finitely many terms. And inside of each, basically I can just cut off the degrees which are higher than 5, so I get a finite sum. Maybe I should try. So to find, let me find the coefficient of, let's say, x to the 4th to be even faster. Only need to consider a finite product. 1 plus x squared, x cubed, x to the 4th times 1 plus x squared plus x to the 4th I don't care about x to the 6th anymore. 1 plus x cubed plus, that's it, times 1 plus x to the 4, and that's it. So I expand this, and I get a finite sum, and I only look at the coefficient of x to the 4, and that's going to be, the claim is that hopefully that's going to be the number of partitions of 4. So you see, even if I'm writing infinite, if I have infinite things on the right and the left hand sides, but still it all boils down to finite computations, like expanding the product of a bunch of finite polynomials. So I need to consider the coefficient of x to the 4 in this product. Okay, and so in general, the proof is very simple. Yeah, first of all, whenever I write such a product on the right-hand side, I have to check first, need to check that the product stabilizes. Which is, all right, so remember, for the product, if you have an infinite product, then you have to, each product is of the form 1 plus g, and then you have to look at the degree of g, not of the degree of 1 plus g. So if you write down 1 over 1 minus x to the j as 1 plus g, then the minimal degree of g is going to be j, because g is equal to x to the j plus x to the 2j plus etc. So this goes to infinity, and therefore the product stabilizes to some valid formal power series. Next, I have to compare the coefficients of x to the, compare the coefficients of x to the n on both sides. So for on the left-hand side, is just number of partitions of n. So let's say so each individual partition contributes just one to the coefficient of x to the n. And on the right-hand side, well, I have to think about the product. So I have to think of my lambda in a slightly different way. And the way I'm gonna, basically what I'm gonna do is I'm gonna look at the multiplicities of my parts. So let m sub j be the multiplicity of lambda sub j, well, multiplicity of j in lambda. So it's the number of parts of lambda which are equal to j. That's m sub j. Then I can write x to the n as x to the m1 times 1 times x to the m2 times 2 times x to the m3 times 3, etc. And most of only finally many terms are not going to be equal to 1. And now the result basically follows. So you just because in the infinite product you pick x to the mj times j out of each term 1 over 1 minus x to the j, which is 1 plus x to the j plus x to the 2j plus x to the 3j, etc. So each individual term looks like this. And since you know the multiplicity, you can pick the correct term on the right-hand side out of each. You can pick the correct term out of in the infinite product, and you can multiply them together to get x to the n. And conversely, if you tell me which term you pick, it doesn't matter. They don't have to be weekly, decreasing, or whatever. You just tell me. Conversely, any partition lambda contributes 1 to the right-hand side. So any partition lambda arises exactly once in this way, because if you tell me, okay, let's try an example. Let's say you tell me to pick some term out of each infinite sum here. So maybe you pick x squared and 1 and x to the 9. Then I can say that that lambda is, so first of all, in the first term j is equal to 1, here j is equal to 2, and j is equal to 3. So I can see that the multiplicity of 3 in my lambda is going to be 3. So lambda is going to start at 3, 3, 3. And there's going to be 0 2's. So there's not going to be any 2's in my lambda. And there's going to be the multiplicity of 1 is equal to 2. 3, 3, 3, 1, 1. That's lambda. And the size of lambda is equal to the sum of these parts. So it's 11. And x to the n is, if you just multiply the corresponding terms, you get x squared times 1 times x to the 9, which is 11. That's how the correspondence actually works. Okay, I have 3 minutes left. Maybe I should... Yeah, next time I'm going to discuss some variations of this approach. And so for example, let's say you're only allowed to take parts. Yeah, there's some... I don't remember if there's going to be a homework problem. At some point there's going to be a homework problem like this, which asks you to, let's say you want to find partitions of n into sizes of, let's say, 1, 2, and 5 only. So you want to count number of ways to split n dollars into $1, $2, and $5 bills, even though some of them may not exist. And then, right, previously we studied general partitions, but we don't know how to do 1, 2, and 5 only. But for generating functions, if just ordinary generated function is going to be equal to, you just take this infinite product. Infinite product allows you to take all parts, but if you're only allowed to take 1, 2, and 5, then you just take the products over. So it's going to be 1 over 1 minus x to the first times 1 minus x to the second times 1 minus x to the fifth. Because these are 1, 2, and 5 are the only parts which are allowed. If you expand the corresponding infinite product, then you just multiply all the terms out, then you're going to get partitions of this kind, with these kinds of restrictions. Or you can also, yeah, I guess it's better to do it next time. Next time I'm going to actually discuss what if you have, so next time, what if you have odd parts only, or what if you have distinct parts only, or whatever else. All these variations can be naturally dealt with using generated functions. So that's it for today. Hope you had a great weekend, and see you on Wednesday.